So hello, I'm Aurore Finco, I'm from Montpellier and I'm of course a PyMoDAQ enthusiast. And so today I'm going to show you how you can use it to analyze some data. So this is a talk I gave at the last PyMoDAQ days and now I'm publishing it. So the idea is that we have some data. And here in this case I chose some scanning and V-center microscopy data because this is what I do, and also because this is data which is 3D. So this will show you immediately why PyMoDAQ is useful. So in all this notebook I'm going to rely heavily on a small package with useful routines that we wrote. So it is very specific to what I need, so probably most of it will not be interesting for you, but if you need to have a look at it or if you want to run the notebook, please clone it on GitHub and have some fun. So the data we are going to look at comes from a scanning probe microscope, so this is images, and so divided in pixels. And at every pixel, we will measure the distance between the tip of our microscope and the surface, and we will also measure a spectrum. And this spectrum is a photoluminescence curve measured as a function of a frequency of a microwave signal. So these spectra, we call them ODMR. You will see some ODMR written everywhere. This is why. And from this spectra, we will find the position of a magnetic resonance of the defect we use to do the measurement, and the position of this resonance gives us the value of the magnetic field that we are trying to measure. So in the end we get a map of the magnetic field. So this is what we want to do with this notebook. So let's go. So first we need to import a bunch of things. This magic line here is very important if you want to be able to use all the interactive viewers from PyMoDAQ. All this is your regular things. This is our custom package, and this is the PyMoDAQ part. So nothing complicated there. And we will need this thing, which is the gyromagnetic ratio of the electron. So first thing we do is, of course, load the data. So we need to find it. So here is what we need. I've put the data somewhere in a folder called data, and I will have basically two data sets, one for the scan, which I called food B here, and one for experience spectrum, which I use as to subtract a reference field. And so this is 1D and this is 3D. Okay, let's go. So we start with the 1D reference spectrum. So our microscope just outputs everything in a text file because this is not a custom microscope that we run with PyMoDAQ, this is a commercial one. But we can nevertheless use PyMoDAQ to analyze the data. So we wrote a small routine that loads everything and fits it directly. And it outputs a data row object, which is a data structure from PyMoDAQ, and it contains the data. If we decide to fit, it contains the fit, and also the initial guess from the fit. Sometimes it's useful if the fitting doesn't work. Okay, so we can do that. Okay, it's loading the data, and here you see I'm printing the labels, so the list of the curves that I have inside this ODMR scan object. And you see I have this row photoluminescence, the fit, and the initial guess. Okay, so let's plot it. And nice thing, this data row object, all these data objects, actually, they have this plot function. You just call it, and you get a plot. This line here is useful because it puts the title at the right position and avoid that you get two plots. So here we are. So the red line is the measurement, the blue line is the initial guess from the fit, the green one is the fit, fits nicely, very good. but maybe I want to play around, know something. So let's open it in an interactive plot. So we use this function here. So we call our 1D viewer for PyMoDAQ, and then we show the data from the object ODMR scan inside this viewer. And there it is. So you have a new window which opened there. So you see, it's the same plot as before. I have my 3 curves. Honestly, I don't care about the initial gets because it worked, so I can just hide it. Little trick here. I can then adjust the zoom. I can have a little cursor here that I can move around and read the position on the 3 curves. So I can say, okay, my resonance is roughly there, 2.8 gigahertz. Okay. Well, this is a regular 1D viewer for from PyMoDAQ. So this was the first easy part. Okay, so I close this. We don't need it anymore. Okay, and well, we can read the value from the fit, convert it in magnetic field. So we have a bias field of roughly 2.5 millitesla. Okay, let's continue. So now we want to look at the sky. So there's a lot of information, actually stored in several text files. So again, we have some nice routines to load everything. First, I load the content of the header, and I read the metadata from this header. And I have this variable here, the list of the channels, because I have many channels actually. I told you we measure the topography, we measure the photoluminescence, the instrument is already doing the fit, which is not exactly what I want, but still I get a map. Well, there are many things like this. So let's have a look. You see, I have 5 channels. So we can load these 5 channels, which are stored in 5 files. But this is done automatically again. And here you see I specify the experiment type. This is also something from the custom package, so that I know what to look for. I know this is 3D, for example, because I wrote full B there. Okay, so first thing we can do is check the list of channels that have been loaded. You see, same as before, everything worked fine. You can have a look at the metadata. You see all the measurement information is there. Like the resolution of the image, you see you have 80 by 80 pixel, the size, 5 by 5 microns, things like that. Okay, so very good. Maybe first thing we can do is plot the field map given by the instrument. So from this, we use this object here, which is called roscan. This is coming from the output of this load function here, and this is a data to export object because it contains several data with access. We have all the maps and we have all the spectral also. So we can get the data by name. We know there's a channel called B field in there because we checked it. And we can plot. There is again this nice plot function that is already there because this bmap thing is the data with access. I just patched a few things to make the display like I want. And here we are. So, nice, isn't it? So, this is a map of a magnetic cycloid measured on a material called bismuth ferrite. Well, it doesn't matter, just beautiful. But you see here, this is not exactly what I want because there is an offset in the data. The average should be at 0 and it's at 25. And 25 watts, 25 goes. And I prefer SI units, so I also want to convert. And so what we're going to do is actually fit again at every pixel the spectrum which has been measured, extract the value of the field like we did here, and subtract this bias field, this 25 curves that we have here to get a 0 in the middle. So let's go. Well, again, we can put everything in an interactive viewer. You remember we have 5 channels, and so there's an object called viewer dispatcher in PyMoDAQ GUI that you can use for that. Well, I modified it a little bit, so we use a custom one. Basically, it's just changing the way it's arranging the viewers. One. So let's go. Here you see I have my 5 channels. Here we are. So we can make it bigger. We can have a look. You see the interesting part is really this field map. The photoluminescence is uniform, which is what we want. We don't want to have a drift, because it means that the setup is not properly aligned anymore. The AFM is pretty flat for these 2 channels, and this is the height. You see we have some jumps because we make some pauses in the measurement, so there's nothing weird there. Everything looks fine, but also not very useful as it is now. So, but you can check your data with this. You can, and again, you have a viewer from PyMoDAQ, so you can have a cursor, you can move it around, you can also open this ROI manager, add a rectangle somewhere, do whatever you like on each of them. Okay, so I don't need it anymore, I close it for now. Let's continue. Let's now open the spectra. So here it starts to be very interesting because the spectra, it's a 3D array. Because at every pixel we have a 1D spectrum. So then we use a viewer ND for that. Let's have a look. So you see here we have the 2D map, so it's a cut or something else. So here at the moment actually it's not a cut, it's the mean value. And here we have a cursor, and if we move the cursor, the display here is changing and we get the spectrum at the pixel where I put the cursor. So let's improve that a little bit. You see here, from what I get from the instrument, I get the data, this green row thing here. I get the fit made by the instrument, which I can trust or not. And I get the standard deviation of the data, which for now is not very interesting. So I can hide it again and adjust my view. And here also you see it's purplish, and this is because we have the 3 channels that are overlapped. Here if I plot only the blue, I plot only the standard deviation, not very interesting. If I plot only the red, I plot only the raw data. So it doesn't look very nice for now, because what we're plotting in the mean is the mean value of this spectrum. Sounds very useless, right? So let's change. And as I told you, the magnetic field is going to be given by the position of this resonance here. So what we need is argmin, actually. And ta-da! There we are. We got roughly the field map again. So this is exactly what we wanted. And now we can move around, and you can, for example, check if there is somewhere a bad pixel where the spectrum is like bad, the resonance is out of the frequency window, the fit doesn't work, something. So this data set is very nice. So it's working at every pixel, but this is a way that you can localize bad data points and have a look at them and decide what you want to do with them. Okay, let's continue. So now we have this, and let's say we want to fit again because we like that, because we want to use another function, for example. So I will run it, and it will take some time. So I have again a small function that can do that. I get a lot of crap coming out in the cell, but we don't care about this. And I have a nice little bar here that shows the progress of the fitting. So we need to wait a little bit for this. But in the meantime, we can maybe look at what's happening next. So what we will get is again a 3D dataset, and for each pixel we will have now the fit that we are doing now. So we can again use a ND viewer and have a look at everything. Check that what we did is better, or at least as good as before. And this will also generate some images that show you the parameters extracted from the fit. So you see we have these objects here, they are coming out of the fitting routine here that I call field flow scan. So we get the spectra and we get the images directly. And you can specify the fitting function that you want. So here we are fitting with a Lorentzian, but we could use a Gaussian, for example. But here the Lorentzian fits better. Okay, so where are we? Almost done. Okay, just need to wait a couple seconds more, maybe a bit more. Okay, should have started that before. Sorry. Okay, almost there. We are done. So now let's open the spectra. So we get again this ND viewer with the navigation, the spectra. So you see now we have basically two more curves, the fit and the initial guess. Again, if you need to fix things, it's useful. The instrumental fit is the curve we had before. The raw data is the white one, and we still have this standard deviation. That is annoying because it's changing the view. Okay, so here we are. So you see I don't see the red because it's actually behind the blue. So here in this pixel didn't change anything. If I move around my cursor, sometimes it's not exactly the same. Well, for this dataset it's not very useful, but sometimes it's nice. So, like before, you can check every pixel. You can get an idea of how your data look like. Very nice. But what I want is images in the end. So let's run this one. So like before, so here what we get is the fitting parameters for every pixel. So I have the amplitude of the Lorentzian, and I have again the parameter and the error. So maybe the error, I don't want to plot it for now, so I can hide them. So this is the amplitude from the Lorentzian, this is the height of the peak that you can derive one from the other. This is the offset, the constant value, so this is actually the photoluminescence. If you remember, it's flat as before. This is the position of the resonance, this is what we are interested in, and this is the line width. You see here it's not changing a lot. Well, no, this is the sigma parameter and this is the line width, so you see here nothing's happening. Sometimes some things are happening and it's interesting. Okay, so still I'm not so happy with this because this is in gigahertz and I would like to have magnetic field. So let's keep working a little bit. So what I can do is post-treat all that I have, convert the parameters that I got from the fit inside physical quantities that could be interesting. So again, I have a little function for that, and it's going to create again data to export with some 2D arrays that I can plot in a viewer dispatcher. There we are. So we have only 4 now. So this one is the line width. So as I told you before, nothing there, but sometimes there is. This is the photoluminescence, again not much there, contrast also not much there, but this one is there. This one is nice, this one is the magnetic field. So let's have a look closer at this one. So let's just stack all the others and focus on this one. Okay, there we are. So you can do a few things. First one is show the color bar, so it is there. And you see it's gray, maybe I don't want to have it gray, so I can change, I don't know. Like this one's fancy, yeah. And you see now I have the 0 in the middle, because in my routine to treat my data, I removed the value that I measured on the reference spectrum. And you see my unit now, this is in Tesla and not in Gauss anymore. Also nicer. So here we are. Something you might want to do on data like this is measure the period of this oscillation. Why not? So to do that, you need to extract a profile. So let's go. So we extract a profile using the ROI manager. We create a rectangular one. So we have it, it's there. So it's in red. So maybe I'll change the color if I can. There, let's make it blue. Well, not so much better. Maybe light blue. Okay, yeah. So let's make it thin. And we can even rotate it to be perpendicular to the stripes. Something like this. Okay, even longer, we can do something like that. So, here you might get a bug by rotating the ROI if you use PyQt graph 0.13, but with PyQt graph 0.14, I did it here, you see it's working. So what we have here is at the bottom we get the average of the ROI along the short side here, so not much because we took it perpendicular. And here we get the average perpendicular to the long edge. And you see that now we have the oscillation, and I can play around. If I make it wider, see it's getting a bit smoother. If I make it thinner, less average, a bit more noise, but the data is already pretty smooth. Okay, so you can play around with the thickness you want here. And now we want to get this profile here. I want this, I want to fit this. I want to know the period. How do I do that? Well, I right click there. And you see I can copy ROI to clipboard. Let's go. And now I go back to my notebook. And there we are. So I have my treated scan object, which is again data to export. So there are several data with access in there. One of them is called B field. It's the 2D array that we were looking at. And I can use this nice thing here to slice. So here, I tried it before, but I'm going to paste my new slice. So this is what I copied from the ROI. So it's exactly the position of the rectangle that we had before. And so if you give that to this function, which is a method of the data with access, it's going to extract directly the 2D array, which is inside the ROI. And now I want some 1D data, so what I can do is already take the mean value, and the number here is the axis. So I don't want to average along the first axis because it was a short one here. I want no, the first axis was the long one. I want to average along the other one. So here I use 1. If I take 0, you will get the you will not get what we want. Okay, let's go. So there we are. This profile thing is already directly another data with access. So you can do all the stuff you like with data with access. For example, plot it. There we are. Okay, it worked. So you have the fields as a function of the position. You get the oscillation. Nice. So now let's fit that. So I define, a sine model with my favorite fitting package, which is called LMFit. So I define a sine model. I have an offset, so I need to add this. I find an initial guess. I fit it. Okay, very quick. It worked nicely. And I can remove that, and I can append this fit that I just did inside my object profile. This is also something nice. If the shape is the same, you can actually just add it this way. So by creating another data with access and appending it to the other one with the label. So my label here is fit. Let's go. Let's plot it. So now we have two lines because we added the fit, and you see it's fitting nicely, and the period is 86 nanometer. Nice. Okay, so I'm done. I know the period of the cycloid in my image. So once I'm done, maybe I want to save my work. So to do that, you can use the nice H5 modules from PyMoDAQ. So you first need to create this saver object, create your file, and node in there, and then you can save your data in there. So there's a specific saver object for the data to export, and another one for the data with access. So I will do this one, for example, and then you have your H5 file here in your folder with your data. So that's it. I hope it showed you a little bit what you can do, gave you some ideas, and enjoy PyMoDAQ.